Hello, this is ReCycle, our bicycle-mounted power generation and charging system. The project motivation behind this is that cyclists often rely on devices such as their phones for navigation, communication, and safety. However, the access to charging stations for these is very limited when you're on long remote rides, such as often these bikers do. Power banks can be useful, but they provide finite energy and do have to be recharged after that's run out. So there's still a need for a system that generates continuous power while cycling. ReCycle does exactly that. It converts bicycle motion into usable electrical energy. It's designed to be lightweight, efficient, and user-friendly so that everyone can use it easily. It also stores the energy generated for a later date so that you don't have to charge your phone always while biking. This provides reliable charging for small devices during these rides. The electrical system mainly comprises of two parts. The first part takes the power generated by the bicycle hub, turns it into DC current, and stores it in the batteries. And then the second half takes that energy from the batteries and uses it to charge your phone. It charges approximately 7% in 5 minutes and takes about 71 minutes to charge the full phone. Some key features that it does is it provides voltage regulation at both stages, has battery protection via a BMS, has a stable 5-volt output, and is accessible to all types of phone charging.
So the first part of the system is when the batteries are getting charged. This is when we're turning the usable motion from a cyclist's pedaling speed into usable electrical energy. And so as the rider moves, the wheel produces a AC signal, and then connecting from the dynamo, we're able to convert this AC signal into DC signal to power our batteries. To do this, we use a bridge rectifier, which is basically made up of four diodes, which converts the signal into DC. We then use a capacitor to smooth out the signal to make sure that the voltage is basically stable and consistent, and then a step-up converter, which is also a charging module for the lithium-ion batteries, which boosts the voltage from whatever pedaling speed and voltage that has been created from the rider up to around 8.4 volts to charge the battery. One thing in the system is that it charges the batteries at over 10 kilometers per hour, which is fine because most average pedaling speeds for riders is 20 kilometers per hour. Before that, though, the phone can still be charged because the batteries are previously charged as well. In the second stage of the system, the stored energy in the batteries is used to charge the phone. So using a 2S2P configuration of four lithium-ion 18650 cells, we get a voltage range of around 7.4 to 8.4 volts. And so to ensure safety, we have a battery management system as well, which basically protects against overvoltage and overcurrent. And so since phones require a stable 5-volt input, we also have a step down converter to regulate the battery output to around 5 volts at 2 amps. And then that step down converter plugs into the phone, or the charging cable, which plugs into the phone. And so the system shows that we can charge a phone by around in 5 minutes, we can charge around 7%. So it'll take an hour and 11 minutes to charge it completely. And this video just shows the system charging the phone.
One of the mechanical components is the phone holder. This has an adjustable ball and socket, two C-clamps, three claws, and a gear. It works by having all of the pieces screw together, and it's compatible with all types of bicycles with different size bars and phones. The third claw goes underneath the phone to hold it in place from vibrations and bumps, and the adjustable claw works by just screwing on the gear. then you can see that this is the printed phone holder, which is mounted onto the bicycle with the phone inside. There are two claws on either side, with a third claw holding it in place with easy access to the charging port. Then we have the electrical enclosure. The outer enclosure enables easy access to the USB and the cables. It is also easily attached to the bicycle through the Velcro straps that are two on the top and one on the side. It has the hole for the USB and cables and the snug fit for the inner enclosure, which then prevents the electronic damage. The inner enclosure has a shelf for compartmentalization of all of the electronic components. It also has a lid which can be sealed onto it so that the battery pack can just be removed whenever. And the outer enclosure has a removable lid for easy modifications and adjustments of all of the inner components. As you can see, these are the 3D printed parts. It's got the removable lid, shelf, the sealing lid for the inner enclosure, and it all fits really nicely. On the right, you can see the enclosure with all the electronics wired into it and mounted to the bicycle.
Okay, so here's a video that's going to show an overview of our electrical enclosure. So you can see the batteries inside of the inner box, the lid that goes on top. You can see this USB port sticking out of it. And then this slides into the outer enclosure, which is going to be attached using Velcro straps. And then Leora in the video is just going to grab a sliding piece, which is just going to slide into the outer enclosure so that everything is sealed. Okay, the next slide or the next video is just showing us the wiring. So you can see from the dynamo, the wires are going to go up into the enclosure, and then the phone charger is going to come out of the enclosure and plug into the cell phone. And then lastly, we have a video of just a demo of our system being used. So here's our group member on a bike. She's cycling, and then once she gets off, she's going to plug the phone charger into the phone, and you can see the charge display come on in just a second. There we go. Okay, so now for an overview of our requirements. We were able to pass the ones that were ease of storage and transport, simple attachment, and simple integration. And then for the lightweight requirement, our total system mass was 0.66 kilograms, where our target was 0.5. But there was a bit of a trade-off between having additional batteries for additional power and weight there. So that's something that can maybe be changed in a future design, but that's what we settled on. And then budget feasibility was passed. Our thing was less than $200. We have a safe electrical output, and the system parts are separated. The output voltage is regulated at 5 volts and 2 amps. And then the only piece accessible from the outside of the box is the charging port, which is always safe to touch. And then battery protection, our system is managed with a BMS to prevent damage. And then we conducted some tests to test durability. We did a vibration test by riding the bike on gravel road. The system remained attached for for over 5 minutes. And we did an impact test where the bike was dropped to simulate crashing conditions, and the whole system remained intact. Then for weather resistance, we exposed the system to rain and mud for over 15 minutes. And there was a water resistance was partially achieved because we had a dual enclosure design. But our hope is that in future iterations there would be we would use more waterproof materials and gaskets for sealing to really improve this. So we said that this was partially satisfied in our design. And then there was no interference with rider safety or comfort, as well as testing steering and braking to ensure safety. We tested before and after installation, and there was no restriction to handlebar movement or braking capacity with our system installed. And then no components interfered with rider movement or comfort as well. So this was passed too. And then the collection of electrical power from bicycle motion, we attached a belt and rotating device to the dynamo hub, and we spun it at various speeds, and then took current and voltage values from this over a known resistive load with a specific power rating. You can see our setup in the photo below. And then we graphed our results above, and it satisfied the requirement, generating 3 watts at the typical bike speed of about 20 kilometers an hour. And this is just an overview of the requirements. You can see the ones we passed and partially satisfied there.
So the next part of our testing was more of the validation section. What questions would users or buyers want to know? So the biggest one, how efficient is this system? We use the same setup with the belt and the drill as in evaluating requirement 1, and we used a known resistive load with the Shimano hub to find voltage and current to test the power. And then we did the same with the electrical system attached, and we found an efficiency value that you can see on the next slide. So this is a graph of the voltage that the hub is generating in blue, and then how much we're getting after the rectifier in red. And at the most common bike speeds between 15 and 25 kilometers per hour, we're at about 45% electrical efficiency. So the next big testing that we did was drag testing. So the method was we ran the bike on a treadmill at a constant speed, and then we lifted it up and let the wheel decelerate naturally. And then we were able to measure the change in voltage over time from this. And with that data, as well as the moment of inertia and some other calculations, we came up with numbers for the amount of power that the drag eats up. And then we did that test with and without the electrical system to compare them. So in red here, we have the drag with the attached electrical system, and then in blue, the base drag, which is the drag with just the hub on it. So some user-friendly values from this information is that at 20 kilometers an hour, you're looking at 3 watts of additional drag from our electrical system. And that translates to about 1.57 additional minutes to bike 20 kilometers if you're usually biking at a 20 kilometer per hour speed. And the charging performance, this is very similar to what our elect team told you. We did some testing of how long it takes to charge the batteries. And from that, the time to charge a phone from 20 to 80%, which is the most linear part, is about 42.9 minutes.
And then in future iterations of our project, like I said before, we'd like to improve waterproofing using sealed materials and gaskets, as well as having like a fully enclosed electrical system with more secured housing. And then develop possibly a user interface or app to see your real-time charging data, and then possibly some instruction manuals as well. And then ideally some expanded compatibility beyond just USB, which was what we currently have, to allow for multiple device connections. And then also exploring alternative materials to improve durability and weight reduction as well. So yeah, I think that's everything. Thanks so much for listening.